In this video, we study quadratic functions, namely functions of the form f of x is ax squared plus bx plus c, where a, b, and c are any real numbers, and in order to ensure we do have a term that contains x squared, we also set the condition that a is not allowed to be 0. Depending on the sign of the leading coefficient a, the graph of the quadratic function is either going to be a parabola that is concave up. If a is positive, then the graph is going to be concave up. If a is, however, negative, then the graph is going to be concave down. The parabola has a special point called the vertex of the parabola where the two arms meet, and depending on whether the graph is concave up or concave down, we're going to have a point of either minimum or maximum at the vertex. If a is positive, then we see that I have a point of absolute minimum at the vertex. What do I mean by that? Any other point on the graph, this one or this one or this one, is going to have a y value that is higher than the y value of the vertex. On the other hand, for the concave down graph, the vertex is going to be a point of absolute maximum, meaning it is a point that has the highest y coordinate of all the points on the graph. If we're interested in determining the vertex of a function algebraically, so if I give you a function rule, how do I find the coordinates of the vertex? And we have a formula for that. We only need to remember the formula for the x coordinate of the vertex, namely it's going to be minus b over 2a. And the y coordinate, we can certainly find a formula for it. However, it's easier to remember that since it is a point on the graph of the function, all we need to do is plug the x coordinate that we obtained here into the function, and that will give us the corresponding y coordinate of this vertex point. So let's look at an example. Let's say that I have the function f of x is 2x squared minus 4x plus 5, and I want to find the vertex of this particular function. So we recall our formula for the x coordinate to be minus b over 2a. So the coefficients of this function are as follows. A will be the coefficient of x squared, which is 2. B is the coefficient of x, and notice I take the minus as well, so it's negative 4. And C, the free coefficient, is 5. So don't forget to include the minuses for these coefficients if they are present. So now let's plug these numbers into this formula. So I have minus, and then b is negative 4, and then divided by 2 times a, which is 2. So I have 4 divided by 4, which is 1. So the x-coordinate of my vertex is 1. For the y-coordinate, all I need to do is plug this 1 back into my function and compute the corresponding y-coordinate. So I have 2 times 1 squared minus 4 times 1 plus 5. So I get 2 minus 4 plus 5, which equals to 3. So my vertex is the point of coordinates 1 and 3. And because the coefficient a is 2, which is positive, my graph is going to be concave up. We can visualize that. So I have a concave up graph, and therefore my vertex is a point of absolute minimum. So let's look at another example, namely f of x is x squared minus 6x plus 8, and let's try to find the vertex as well as the x and y intercepts of this function and use these to graph the function. So we start by looking at the vertex. So for the vertex, we have the formula, the x-coordinate of the vertex is going to be minus b over 2a. So in this case, minus negative 6 over 2 times 1, or 6 over 2, which gives me 3. So the x-coordinate of the vertex is 3. So now let's compute the y-coordinate of the vertex. Let's plug 3 into my function, and I get 3 squared, so 9 minus 3 times 6 is 18, plus 8. So 9 plus 8 is 17, so we get negative 1 for my overall answer. So I get that the vertex is the point of coordinates 3 and negative 1. We also note that since a, the coefficient of x squared 1 is positive, then I'm going to get a graph that is going to be concave up. So I have a point of minimum for my vertex. In terms of the intercepts, so let's look at the x-intercepts. We set the y-coordinate equal to 0 because we want points on the x-axis. So we get the equation x squared minus 6x plus 8 is 0. And we need to solve it. So we're going to do so by factoring. So we're looking for two numbers that multiply to 8 and add to negative 6. So 8 is positive, and since the sum is negative, that tells me both numbers have to be negative. And 4 times 2 gives me 8, and 4 times 2 also gives me 6. So I'm dealing with x minus 4 and x minus 2. Negative 4 times negative 2 is 8, and negative 4 plus negative 2 is negative 6. So I have the right numbers, and that gives me the solutions. X1 is 4 and x2 is 2. So the x-intercepts, these are the zeros of the function, are going to be points, namely the point of coordinates 4, 0 and the point of coordinate 2, 0. Finally, let's find the y-intercept of this function. So we're going to find the y-coordinate corresponding to the x-coordinate of 0, and that's going to give me 0 squared minus 0 plus 8, and that just gives me 8. So the y-intercept is the point of x-coordinate 0 and y-coordinate 8. So let's plot now these points on the graph of my function. So first, the point x is 0, y is 8, is over here. The next point is at 2 and 0, this is an x-intercept, and at 4 and 0, and that is a y-intercept. And finally, I'm looking at the vertex, which happens to be at 3 and negative 1. If this is negative 1 and this is 3, that happens to be the vertex of my function. So now all I have to do is draw the parabola through these 4 points. So we have the x-intercepts, the vertex, which is a point of minimum, and the y-intercept. And using these points, we get a pretty good estimate of our graph. Namely, we have a concave up parabola. We now focus on solving quadratic equations, namely equations of the form ax squared plus bx plus c equals 0. So far, every example that we've encountered, we solved by factoring using one of the 3 techniques that we learned, namely the technique of factoring out the common factor, which is this case. If I have x squared minus x equals to 0, we can pull out the common factor x, and we get x times x minus 1 is 0, and of course the solutions that we obtained here are 0 and 1. We also had the technique of the difference of square formula, a squared minus b squared. Here, x squared minus 1 equals to 0. We can factor again, x minus 1, x plus 1. So we get the zeros plus or minus 1. And finally, the sum and product technique for factoring. If I have, say, x squared plus 3x plus 2, two numbers that multiply to 2 and add to 3 are 1 and 2. So in this scenario, we get the zeros negative 1 and negative 2. However, these are only some very simple examples, and the vast majority of quadratic equations cannot be solved using these three simple factoring techniques. So we are in desperate need for a universal technique, one technique that applies to all quadratic equations. So this universal technique is going to rely on the quadratic formula, which we're going to use to solve quadratic equations, namely equations of the form ax squared plus bx plus c equals to 0, where a is not equal to 0. First, we're going to introduce a quantity called the discriminant, and we're going to denote the discriminant by the Greek letter delta, and its formula is going to be b squared minus 4ac. Now this discriminant, and therefore its name, is used because it discriminates between the number of solutions that a quadratic equation has. And we'll see why in a minute. Using this discriminant, we're now going to be able to find the solutions of the equation if it has some, namely x1 and 2 is equal to minus b plus or minus the square root of delta over 2a. So let's now understand how this discriminant delta tells me about the number of solutions for a quadratic equation. So let's analyze this formula here and see what delta tells me. Well, first, let's notice that in the case that delta is less than 0, then what we obtain is that because delta is plugged under an even root, we do not have a defined operation there. So we can't plug a negative number under an even root. Therefore, in this case, the equation will have no or 0 solutions. If delta equals to 0, then how many solutions are we going to get? Well, we have a plus or minus here in the formula, and that really is the source that's going to give me two solutions, one with plus and the other one with the operation of minus. However, if delta is 0, square root of delta is also 0, so if I add or subtract 0, it's not going to really change my solution. So in this case, the solution is going to be unique. I have one solution, and it's going to have the form of minus b, well, plus or minus 0 doesn't change anything, divided by 2a, and interestingly, it is actually the formula for the vertex for a very good reason. Finally, the third case we have when delta is strictly greater than 0, and then this plus and minus will really play a role, and we're really going to have two solutions. Namely, the first one, x1, will be minus b plus square root of delta over 2a, and the second solution, x2, will be minus b minus square root of delta over 2a, and that's why we write this formula together as x1 comma 2, because we want to use shorthand notation and simply understand one solution is with plus and the other solution is with minus. So now let's look at some examples of equations and use the quadratic formula to solve them. So let's say I have x squared plus x plus 1 equals to 0. Now we could try and factor using our usual technique of sum and product. However, there are no two numbers that multiply to 1 and add to 1. And the quadratic formula will guarantee and show me that this is really the case. I don't need to really try. If at all I have any doubts, I can always go back to the quadratic formula because it will always tell me the number of solutions that I will have. So let's start by computing delta, namely b squared minus 4ac. It really is important that you remember this formula, not approximately, but really the exact formula. So write it down a few times. So in this case, b is 1, a is 1, c is 1, so I get 1 minus 4, which is negative 3, and that means delta is less than 0. So, as we saw before, if delta is less than 0, because I can't plug a negative number under an even root, my equation has no solution. Let's look at another example. Let's say x squared minus 6x plus 9 equals to 0. Again, we start by computing delta separately. And let's say I have negative 6, everything squared. Notice the minus is inside the parentheses. Minus 4 times 1 times 9. So I get 36 minus 36, which is 0. So automatically I know I have one solution. And what is that solution? Well, the quadratic formula now tells me minus b. I will have this plus or minus 0 over 2a. So just minus b over 2a, which in this case is minus negative 6 over 2 times 1. So I get 6 over 2 or 3. So the solution of the quadratic equation is a single one, namely at 3. And we could have seen this in this case by factoring, namely this factors into x minus 3 squared equals to 0. Always, when you have the discriminant equal to 0, you will be able to factor your expression into a perfect square. Finally, let's look at another example. Let's say 2x squared minus 6x plus 3 equals to 0. So again, we compute the discriminant b squared minus 4ac and obtain negative 6 squared minus 4 times 2 times 3. So I have 36 minus 8 times 3 is 24. So my discriminant is 12, which is positive. Since my discriminant is positive, then I'm going to have exactly two solutions, and I can write down what these solutions are. So x1 comma 2 is going to be, let's write down the formula, minus b plus or minus square root of delta over 2a. So minus b is minus minus 6, so 6, plus or minus square root of 12 over 4. Now we can certainly simplify this, but for our purposes, for now, that is enough. So, looking at the discriminant again tells us very important information about the number of solutions that I should expect. If delta again is less than 0, my equation has no solution. If delta is equal to 0, I will have exactly one solution. And finally, if delta is strictly greater than 0, I have two solutions. And in both these cases, the quadratic formula tells me how to compute my zeros. This is a universal technique because it always works. Speaking of delta, this discriminant tells us more in terms of not just equations, but in terms of functions, and we'll see in a minute also in terms of factoring. So now let's look again at this discriminant for what it told me about equations and try to deduce what this discriminant tells me about functions. So in the case of quadratic equations, namely the equations of the form ax squared plus bx plus c equals to 0, we saw that the discriminant delta, if it was negative, then I had 0 solutions. A discriminant equal to 0 told me that that plus or minus variation did not play a role, so I had exactly one solution. And finally, if delta is a positive number, then I had two solutions. So let's just pause and understand that really here, this is a polynomial of degree 2, and we have an equation, and it's not necessary that you have two solutions for a quadratic equation. You actually can have 0 solution or one solution. How does this translate for the graph of functions, quadratic functions of the form f of x is ax squared plus bx plus c? Well, if delta is less than 0, then the graph of this quadratic function is going to look as follows. Depending on a, it's either going to be concave up or concave down, but that doesn't really matter here. What I'm interested in is the number of x-intercepts. So if I'm looking at x-intercepts, because in order to find the intercepts, I really need to solve the equation, right? To find where the graph crosses the x-axis, I need to find where y is 0. So I am solving this equation. So if delta is less than 0, that tells me the graph of my function does not cross the x-axis. It's going to not touch the x-axis. So I have 0 x-intercepts. If I have one solution, then I know that when I solve this equation to find where the zeros of my function and hence the x-intercepts, I will get exactly one solution. So what does that mean for my graph? That means my graph touches the x-axis only at one point, and that happens at the vertex. So in this case, I have one x-intercept. And finally, what's going to happen when delta is greater than 0? Then I'm going to have, of course, 2 x-intercepts, and so my graph will cross the x-axis twice. So we see that this discriminant, while it tells me the number of solutions in the case of an equation, it also tells me about the number of x-intercepts for the graph of a function. Finally, this discriminant is very powerful because it's also going to tell me something about algebraic expression. Namely, very often we ask ourselves, does an expression factor or not? And we might be trying to factor it for a while before we get an answer. Maybe we can't think of an answer, but there really is a factored form. So the discriminant is going to enable me to determine whether an expression factors or doesn't factor. How am I going to know what the connection is? Well, let's think a little bit about factoring. Why does it help to factor when we solve an equation? So let's look at the equation x squared minus 6x plus 8 equals to 0. First of all, the most important underlying idea for solving equations is that on the right hand side I need to have a 0. The whole idea of factoring relies on a property that the number 0 has. So you always want to make sure when you solve an equation that you have 0 on the right hand side. Now, once I factor, namely I break this expression into a product of simple parentheses, in this case x minus 2, x minus 4 equals to 0, why does it help? Well, I'm using the property that if a times b equals to 0, the only way that's going to be accomplished is that if either a is 0 or if b is 0. If neither of them is 0, say one is 5, the other one is 6, 5 times 6 is never going to become 0. I really need either a or b to equal to 0. So this is what I'm doing here. I'm taking advantage that either the first parenthesis has to be 0 or the second parenthesis is 0, and that enables me to just locally look at each parenthesis and see what makes these 0. So I get that x1 is 2. And then x2 is 4, because these are the two numbers that make each parenthesis 0. This, of course, will not work if I don't have a 0. Say if a times b equals to 1, there are quite a lot of numbers you can multiply. 5 times 1/5, 100 times 1 over 100 to give you 1. So 0 really is essential in having on one side of the equation in order to solve. Why is it that we factor? It's because we're able to just read off the solution for the equation once we have these linear parentheses multiplied that give me 0. So as soon as we're able to factor an expression, we are going to have a solution to the equation. So let's write this down. So as soon as we are able to factor, say x minus 2 multiplied with something else that equals to 0, we know that x equals to 2 is a solution to the equation. So factoring is intrinsically linked to solving an equation. For that reason, going back to the discriminant, what I have is the following. If delta is less than 0, then the algebraic expression x squared plus bx plus c does not factor. The reason for that is that if I were to be able to factor, as soon as I'm able to split it into a product of two linear parentheses, I have solutions. So knowing that delta is less than 0, I guarantees that an expression doesn't factor. So let's look at an example. Let's say x squared plus x plus 1. Does this expression factor? Maybe there are two numbers that multiply to 1 and add to 1, and I just can't think of them. Well, delta will tell me for sure. So b squared minus 4ac is going to be 1 squared minus 4 times 1, which is negative 3 less than 0. So this expression I now know for sure does not factor, and that's what this discriminant also tells me in the case of algebraic expression. On the other hand, if delta equals to 0, the expression will factor into a perfect square with possibly a coefficient of a in front of it, and if delta is strictly greater than 0, the expression will factor into an x minus x1 and x minus x2, and x1, x2 being the solutions, and possibly you get, if a is not 1, the coefficient of a in front of it. In fact, this is a form that always works when you try to factor an expression. So again, trying to understand this delta, it's really important that we understand what we use it for. If delta is less than 0, then I will have, in the case of equations, 0 solutions. In the case of functions, 0 x-intercepts. And in the case of algebraic expression, the expression will not factor. If delta equals to 0, I will have one solution, one x-intercept, and the expression does factor into, however, a perfect square. And finally, if delta is greater than 0, I will have two solutions, two x-intercepts for the function, and again, the expression will factor. Finally, I want you to understand the relation between a factor and a zero of a function. So if we have a function that's been factored, say 2 times x minus 2 times x plus 1, knowing that x minus 2 is a factor, a parenthesis in this quadratic function, that tells me immediately that 2 is a zero of the function. Namely, if I plug 2 in that function, I get 0, and vice versa. Very often we're going to be plugging, especially in calculus when computing limits, the number 2 into my function, and I will get 0. That tells me, knowing that when I plug 2 into my function I get 0, that tells me that my quadratic function must absolutely have a factor of x minus 2 present if I were to factor that expression.